Hey, what's up everyone? Today we're going to be talking about three-dimensional coordinate systems. Let's get started. To really understand three dimensions, let's go straight to the basics. We all hopefully know what a number line is. And in calculus and other higher-level math courses, we call this R1, or the real number line of one dimension. Plotting points on the number line is super easy. We can do x equals 0, x equals 1.5, x equals 4, etc., etc., etc. Now let's bring this a step up. We all know the xy coordinate system. We can think of this as two real number lines mashed together. We call this R2, or the two-dimensional coordinate system. When plotting points, it isn't enough to just put x points. Each x coordinate must have a corresponding y coordinate to make a point on R2. Some examples are 0, 1, negative 1/2, 0, and 4, 3. Now that we got the review out of the way, let's introduce something new. We have the x-axis and the y-axis. Now let's introduce the z-axis, and we're going to call the whole coordinate system R3, or the three-dimensional coordinate system. The direction of positive z is determined by the right-hand rule. We can think of this coordinate system as three number lines mashed together. Similar to what we saw earlier, when plotting points, it isn't enough to just put x and y points. Each x-coordinate and y-coordinate must have a corresponding z-coordinate to make a point. Some examples are 0, 1, 0, negative 1/2, 0, 1, and 4, 3, negative 2. Let's do an example together. Plot x equals 1 on R1, R2, and R3. We hopefully should be able to do R1. On R1, x equals 1 is just a point. Now in R2, it's a little bit more difficult, but definitely doable. Note that to fulfill the equation x equals 1, we need to find all the points on this graph such that the x-coordinate equals 1. We see that at 1, 0, but also at 1, 1, 1, 2, etc., etc., etc. And we also see it at 1, negative 1, 1, negative 2, etc., etc., etc. Thus, this vertical line is the graph of x equals 1 because all these points fulfill x equals 1 regardless of y value. Now let's plot x equals 1 on R3. Again, we need to find all the points such that x equals 1. Looking back at the horizontal line that we drew in R2, we see that this line works at z equals 0, but it also works at z equals 1, z equals 2, etc., etc., etc. And it also works at z equals negative 1, z equals negative 2, etc., etc., etc. Thus, we can construct a plane. This plane fulfills x equals 1 regardless of the y value and the z value. After all that fun, you may be wondering, is going up one dimension really that nice and easy? Well, the short answer is pretty much. A lot of students overthink three dimensions, but the concept is fairly simple. That simplicity is found in the distance formula. Let's compare the distance formulas in R1, R2, and R3. We know that the distance formula in R1 is d equals the absolute value of x1 minus x0. And we know from earlier courses that the absolute value can be rewritten as the square root of the inside square, or the square root of x1 minus x0 squared. We'll compare this formula with the distance formula in R2, which follows from the Pythagorean theorem. D equals the square root of x1 minus x0 squared plus y1 minus y0 squared. Look how similar these two look. They're basically identical with the exception of this y component. Based on this pattern, we can guess the distance formula in R3. If you haven't figured it out already, it's d equals the square root of x1 minus x0 squared plus y1 minus y0 squared plus z1 minus z0 squared. Again, this formula is essentially identical to the R2 one, with the exception of this z component. This is an important formula in multivariable calculus, so make sure you remember it. Now on your own, try to do this example. And when you're ready, click here for the answer. And remember everyone, understanding the concepts is only half the battle. Make sure you do plenty of practice to really hone these skills and master the material. Thanks for watching.